Hello, everyone. Welcome to this keynote, and it's my pleasure to introduce Professor Pierluigi SIANO, and he's going to deliver his talk to us. There's an opportunity for questions and answers at the end, but if you'd like to put them in the chat at any point, we'll pick them up and then we'll pass them on to the professor at the end. Thanks, Professor. Over to you.
Thank you very much for your nice introduction. Good morning, everybody. I am very happy to present this keynote at this International University Power Engineering Conference, UPEC 2021, and I am grateful to the organizers for the invitation. Today I'm going to present this keynote titled Distributed Parallel Optimization for a Large-Scale Aggregation of Prosumers. In this presentation, after briefly introducing the benefits of energy communities and the procurement of energy flexibility resources in the ancillary services market, I will present an architecture for the large-scale aggregation of prosumers that we designed and developed at the University of Salerno in the context of an Italian pilot project to allow a community of prosumers to participate in the ancillary services market for providing energy flexibility. And we will consider, we have considered both the aid and real-time optimizations. Then I will describe a new distributed parallelized linear programming based optimization that is scalable and privacy preserving. I will also present some results based on an Italian pilot project. And finally, I will present some findings and conclusions. As known in a smart grid, prosumers can aggregate in the so-called energy communities that are also based on the exchange of bidirectional flows of energy and peer-to-peer electrical energy exchanges in order to achieve self-consumption of renewable energy and also to provide the services to the system operators. By participating in the energy community, prosumers take a new role in the energy transition, and they can improve also their economic convenience and sometimes comfort, while contributing to the grid efficiency and stability. Prosumers, in fact, in an energy community can improve the exploitation of renewable energy that is produced inside the community by maximizing the renewable energy self-consumption, also in this way reducing energy cost. These benefits can be further improved by carrying out peer-to-peer energy exchanges inside the communities. Even if these activities allow to achieve economic benefits for prosumers, there are also other drivers for the development of energy communities. In particular, it is important to consider their flexibility potential that is based on some flexibility sources shown also in this. Some of them are shown in this slide. They include demand response, energy storage systems, also considering electrical vehicles in the community, in fact, by contributing to the provision of ancillary services to the system operators, energy communities may increase their economic benefits. In this new model, the provision of ancillary services to the transmission system operator should take into account the possible flexibility that is furnished by new distributed resources, such as dispersed and small generators, also based on renewable sources, and frequently endowed with small batteries. In particular, battery storage projects are becoming in the last years more competitive if compared with traditional interventions, including, for example, the building of new power lines or new power transformers. This is mainly due to the falling of battery cost. In particular, distributed battery energy storage systems, also of small scale, that were mainly used to decrease the uncertainty due to renewable energy sources, while increasing also energy self-consumption, can be also used to provide energy flexibility to the system operator. They can be directly managed by the system operator or controlled by an aggregator or an energy manager, uh, an energy community manager that can offer energy flexibility in the ancillary services market. In this new model, in this context, the European regulatory framework has opened the ancillary services market also to distributed energy resources, including energy storage systems and demand response providers. Among these distributed energy resources, battery energy storage systems have gained recently more attention due to the higher amperage rate and fast response. The proposed methods consider both the planning and real-time sessions to respectively define the unit commitment and the activation of flexibility resources, considering the Italian ancillary services market, where we have a pay-as-bid mechanism and a settlement period of 15 minutes, where, for example, an aggregator, after carrying out a day-ahead optimization based on day-ahead forecast, can offer services of flexibility both in the up or down mode during the planning session, considering its baseline as a reference. If these offers are accepted by the system operator in the ancillary services market, this last can ask the aggregator to deliver the flexibility provision during the real-time session. So if the energy is not delivered according to the day-ahead offer, an imbalance cost is applied. And for this reason, the aggregator should also carry out real-time optimization based on short-term forecasts in order to not pay the imbalance cost. It's worth noting that the Italian Regulatory Authority for Energy implemented a new regulation that allowed aggregated distributed energy resources to participate in the ancillary services market. According to this new regulation, there is no limit related to the rated power of a single resource, including generators, loads, battery energy storage systems, and electrical vehicles. But there is only the constraints that the overall minimum regulating power should be lower than a given value. In this case, nowadays it is 1 megawatt, but it is expected that this value will be lower in the future. Considering this new model, we have developed in collaboration with an Italian company an Internet of Things based architecture for an energy community or an aggregator, in which we have that each residential unit is connected to a gateway. This controlled by an energy management system that has been implemented on a modified version of a Raspberry Pi 3 microcontroller, and is in communication with the energy community manager or the aggregator by means of an interconnection layer consisting of a cloud server, a home gateway manager, and a centralized database. The users or prosumers can connect to the energy management system by using a web app through the cloud. And there are some smart devices that are connected to the energy management system by means of wireless communication, mainly Z-Wave or Wi-Fi. And the centralized database can register the electrical energy consumption of all electrical loads and the generation of, for example, of photovoltaic systems of the users. Also, it is possible to carry out optimization and management activities by the aggregator or energy community manager. Um, Here, there are some smart devices that have been connected by means of wireless communication to the energy management system. Here in the center of this figure, these are all commercial devices that have been including in the system. Also, other devices can be connected by developing the required software. For example, we have implemented some rules for energy saving, considering a boiler by using a smart thermostat and a smart switch. Both are connected by means of Z-Wave um, communication to the energy management system. These rules have been implemented by using a Blockly wizard programming editor, as shown, for example, here in this slide. Another example is shown here for the control of a smart lamp in connection with a light sensor, both connected by means of Z-Wave communication to the energy management system. Other rules can be implemented for a security system, for example, with some sensors and a siren, and a schema and rules for the maximization of renewable energy produced by a photovoltaic system by using two smart meters shown here and a smart plug. This Internet of Things architecture has been further developed to become a transactive management infrastructure for an energy community manager. More details can be found in this paper. The motivation behind the development of these architectures are that in local energy market managed by an aggregator or an energy community manager, prosumers and consumers can trade energy and flexibility within the energy community in a peer-to-peer way. Peer-to-peer may refer to both the way according to which energy transactions take place and to the information architecture supporting them. Blockchain enables peer-to-peer transactions in a decentralized way, perfectly fitting the idea of making energy transactions without the need of a central authority. Also, blockchain can offer a platform to host transactive energy markets where prosumers can directly buy and sell energy with each other. The decentralized control essential for transactive energy is analogous to the centralized consensus of blockchain, and both share the target of opening and democratizing markets. There are some advantages related to a decentralized architecture, including scalability, resiliency, adaptability, fault tolerance, security, and trust if compared to a centralized one. In this slide, we can see the implemented infrastructure where we have three layers. It is these are the data center layer owned by, for example, the aggregator. It consists of a set of servers which are centrally managed by the aggregator. The communication layer consisting of all components to let the transactive controllers communicate with one another, and the user layer where we have all the algorithms and the communication devices. Then the considered architecture has been has been used to manage a large-scale aggregation of prosumers, and this is necessary to evaluate the absorbed, for example, to evaluate the absorbed and injected active power for all prosumers, and to allow the exchange of information between prosumers for managing all the batteries to provide flexibility in the ancillary services market. It has been assumed that all prosumers are endowed with a home device gateway, smart meter, and an energy management system. In this case, the architecture consists of a physical layer and a virtual layer. It is essentially a virtual platform where a prosumer can access. The physical layer provides grid connection, smart metering, and communication to all prosumers. The virtual layer includes an energy information system, allowing local site awareness based on real-time monitoring and on tools for the forecasting of photovoltaic production and load demand. By accessing to the virtual layer, prosumers can exchange only some privacy preserving information related to their local optimal solutions and their power flexibility contribution to fulfill the global constraints of the global optimization problem, as I will explain in the following. And the virtual layer can be also based on distributed ledger technology and smart contracts. In particular, we have considering a day-ahead optimization, where the aim of the aggregator or energy community manager is that of maximizing the remuneration due to the provision of energy flexibility in the ancillary services market, and this is subject to some constraints related to the minimum capacity that should be offered. There are also some local constraints for each prosumer, power balance, power limits from to the grid, power charging, discharging speeds of a battery. And then if this offer is accepted by the system operator, the aggregator should guarantee the provision of the energy flexibility accepted. So in real time, we have the same, in the real time optimization problem, we have the same objective function as in the day-ahead, but with some equality constraints and local constraints. This is carried out every 15 minutes, and it is based on real-time forecast. About the decision about related to the time to the period when this flexibility is provided, is offered and provided, these discrete variables can be identified in two ways: by considering a centralized approach based on mixed integer linear programming optimization, or in a heuristic way by considering a new hybrid variable neighborhood search and distributed parallel optimization. We have used the second approach because in some cases the centralized formulation is not able to deal with very large numbers of real-world scenarios, while by solving the optimization in a heuristic way, we can achieve a framework where all prosumers can participate in solving their local optimization and in solving the global problem in a faster way, also keeping their information not disclosed. The way we accomplish this mission is by breaking down the centralized problem into many linear programming formulations and solving the resulting linear programming problems in a distributed parallelized way. So we have developed a new distributed optimization based on linear programming that overcomes previous models based on integer and quadratic programming. It is scalable allowing to deal with hundreds of thousands of prosumers in real time. It is privacy preserving. In fact, a global solution can be found without any prosumer knowing the behavior or objectives of any other one. It can be implemented by using the described architecture, where each prosumer performs an optimization based on its specific objective function. As regards with the distributed parallelized linear programming based optimization, we consider the minimization of this function. The idea is that of distributing the right-hand side of the global constraints among all prosumers in such a way so that the minimum power flexibility contribution of each prosumer is determined by the energy reserve available in its battery according to this equation. And we solve this optimization problem where the update of gamma is achieved in the virtual layer. The basic intuition behind this formula is that to increase the weights by larger amount, the weights in gamma, by larger amount on those constraints which are more violated. Now I will show some results. First, the first ones are related to the centralized approach. More details can be found in this paper. Particularly, if we consider a large-scale energy community of 2,000 residential users endowed with a controllable photovoltaic battery system, we can see here the state of charge of all the batteries during a day in April, considering up regulation, the aggregation is providing up regulation from 2 p.m. To 6 p.m. In the lower part of the figure, we can see the average power in a quarter of an hour related to photovoltaic generation here, and the absorbed power for the baseline and the absorbed power in the case of upper regulation. Now I will present a similar case considering the scalable privacy preserving distributed parallel optimization. More details can be found in this paper. Also in this case, considering an energy community of 2,000 prosumers, we can see a comparison between the centralized and distributed approach. This is the optimization. Also in this case, the regulation is provided for 4 consecutive hours from 2 p.m. to 6 p.m. If compared with centralized optimization, the day-ahead distributed optimization can achieve the same flexibility in terms of delivering the energy in the measured period and the same value for the objective function. Considering also the impact of the forecast error, we have assumed a 20% error for forecast of electrical load and 10% forecast error for photovoltaic production. Here we can see the absorbed powers related to the ahead to the real-time optimization. And we can say that regardless of the forecast error, the parallel real-time optimization can achieve a power profile very close to that accepted during the day ahead in the ancillary services market. Also, if we consider the computational time of the day, the optimization shown in this figure by varying the number of prosumers in the month of June, we can see that it is very fast along to deal with hundreds of thousands of prosumers in few seconds. Also, when considering the real-time parallel optimization, the computational time varies between 13 and 25 milliseconds when considering the different days of the year. Now I will give some final comments. I would like to highlight that linear programming based parallelization enables not only to perform in enormous real-time way for very large scale real-world problems, but also to fulfill the privacy of prosumers. Both they aid real-time optimizations, being highly scalable and able to protect the personal information of prosumers, overcome typical drawbacks of centralized methods. The proposed linear programming-based optimization methods can be easily coded up and implemented on microcontrollers and connected to the implemented layer architecture. Here there is a list for further selected readings on this topic. Thank you very much for your interest and attention. You can also contact me by email if you have any questions, and now would be interested to hear from you with your thoughts and questions. Thank you very much.
Thank you very much, Professor. Yeah, we have got several questions that have come in through the participants, and if you don't mind, I'll just ask them to you. I think this one's maybe something to do with the network stabilization question. It's to do with the battery storage in terms of locations. Is the battery storage in urban areas or rural areas, or a mixture of the two?
Yeah, yes, thank you very much for your question. Yeah, considering the energy storage systems are related to residential prosumers, assumed in a city located in Italy, and they are sized according to the size of the photovoltaic system of the user, and also this photovoltaic system is sized according to the energy consumption of the user during the year. So it is we tried to consider as much as possible realistic data because the main aim of the optimization is to decide if it is convenient from an economic point of view for the aggregator to make the offer, because it is worth noting that it is not always convenient to make the offer over the year. For example, when the photovoltaic energy production is low during winter, in these cases maybe it is not convenient.
Yeah, thank you. On a similar sort of theme, you mentioned something about economics there, I think. So another question that we've had is, are there any conflicts between saving energy and saving money?
Yes, a very good question. Thank you very much. This is another important issue to consider that we have considered this. What would be the impact of providing energy flexibility to the system operator on the energy self-consumption? Because it is important to evaluate this aspect, and in order to consider this aspect, so in other words, that this will decrease the energy self-consumption for the users and have an impact on both energy and the cost paid for energy. So we need to find a compromise solution between the revenue deriving from the participation in the ancillary services market and the increase in cost in the cost for the end user.
Thank you. At the moment, we've got one other question, and again, I would encourage participants, if they do have questions, to put them onto the Hoover chat, and we can pick them up. But another question that we had in the one of the slides that you showed, the residential Internet of Things based architecture, I think it was phase 1. Do you see that there's maybe a primary limiting factor on there? So, for example, would the home gateway be the primary limiting factor, or something else on there?
Do you mean from a technological point of view?
Yes, yes.
I think from a technological point of view, we can easily implement this architecture. We need a smart meter. So I think actually the weak point is related to the metering. That we need to have accurate metering every 15 minutes. That should be communicated to the system operator. As regards with the architecture for the bus system and the devices required for the users, it is one other important aspect to consider is to have the proper device to control the batteries um, in real time, also to compensate with the variation of photovoltaic production and the electrical loads. And I know that some industries are working on this to design proper devices for controlling the energy batteries of different producers, because it should be we need a device that is able to connect with the different batteries made by different producers.
Okay. Yes, thank you. We've had one more question that's come up. For real-world implementation, the speed of change is happening in terms of communication technology in recent years. What impact do you foresee originating as a consequence of that?
Yes, thank you very much. This is also an important issue to consider. What will be the impact of communication delay on the process, and we think that the proposed approach by considering a distributed optimization where each user can carry out his local optimization. This will reduce the exchange of data between each user and the virtual layer, because we have that each user will carry out a local optimization. So in this case, it is only required to exchange for example, in this case, the value of the exchanged power with the grid. So in this case, we succeeded to parallelize the optimization of all the users. In other cases, when we consider, if we consider also peer-to-peer energy exchanges, this can become an issue, because it is not possible to parallelize according to what we are working on. We did not succeed to parallelize the whole optimization of a single user, but only some calculation. So in that case, it is important to consider how many communications are required for this optimization. So this, in that case, it can be an issue in real-time optimization.
I don't think we don't have any further questions, I don't think. So, oh, sorry, we do have one further question. Energy informatics and big data analytics means new roles for a lot of data managing companies. Again, where do you see the impact of that?
Yes, I think as known that we are nowadays in a big data how to say, the big data era. So we have many data that are generated by smart devices and communicated by each user, and this a huge amount of data should be analyzed by proper systems, also in the case of energy, of electrical energy. So it's also important to develop new methods to extract the right information related to data. So it will be and will be a hot research topic also in the future, I think, both for university and industry.
Yeah, I think that's it. Thank you, Professor. So I think it probably just falls on to me to say thank you very much for the presentation. Really informative, really interesting, obviously key to the kind of time that we're in at the moment, and also for the thorough answers to the questions. Again, thanks for taking the time for that.
Thank you very much. Thank you for inviting me.
The local organising committee and the wider UPEC community, thank you.
Thank you very much for inviting me. It was my pleasure.
Thank you.
Have a good day.